July 1st, 2025, a telescope in Chile detects movement, not an asteroid, not a satellite, something traveling at 61 kilometers per second from a direction no object should be coming from. Within 72 hours, observatories on 6 continents received the same instruction: track it. Don't stop tracking it. NASA says there's no danger. The trajectory is clear, the distance is safe. So why did defense agencies quietly retask military satellites? Why did the International Asteroid Warning Network launch their first ever systematic campaign for an interstellar object? If 3I Atlas poses zero threat, why does Earth's response look exactly like preparation for something we can't afford to ignore?
The Asteroid Terrestrial Impact Last Alert System wasn't looking for history when it scanned the sky on that summer night. ATLAS exists for one purpose: detecting objects that might collide with Earth before it's too late. 4 robotic telescopes scattered across the globe, scanning, cataloging, calculating trajectories. Routine work, protective work, the kind of vigilance that happens in silence until it doesn't. The observatory in Rio Hurtado, Chile, operated under observatory code W68 at apparent magnitude 18, roughly 4,000 times fainter than what the human eye can detect. Something appeared in the data. Moving. Fast. The object sat on the border between the constellations Serpens Cauda and Sagittarius, near the galactic plane where stars crowd the view and make detection difficult. Initial designation: A11PL3Z. Temporary, clinical, the kind of label you give something before you understand what you're actually looking at. Within hours, the discovery observations reached the International Astronomical Union's Minor Planet Center. Standard protocol: log it, verify it, calculate the orbit. Except the preliminary numbers suggested something that made controllers pause. The object appeared to be on a highly eccentric path that might come close to Earth's orbit. Close enough that the Minor Planet Center immediately listed A11PL3Z on the Near-Earth Object Confirmation page. That's the list reserved for objects requiring urgent follow-up, objects that matter. Observatories worldwide received the alert. Professional telescopes, amateur networks, anyone with the equipment to confirm or deny what Chile had found. The Zwicky Transient Facility in California searched their archives. They found it: pre-discovery images from June 28th and 29th, then earlier observations from June 14th through the 21st. Atlas's own systems revealed more sightings dating back to June 5th.
By July 2nd, 3 separate observatories confirmed what initial data had only suggested: the Deep Random Survey in Chile, Lowell Discovery Telescope in Arizona, Canada-France-Hawaii Telescope at Mauna Kea. All 3 detected the same thing: a faint coma, a cloud of gas and dust surrounding a central nucleus, a tail-like elongation stretching 3 arcseconds. Not an asteroid, a comet. But the trajectory told a different story. Follow-up observations revealed the orbit wasn't elliptical like the comets humanity had studied for centuries. It was hyperbolic, unbound, the mathematical signature of an object not captured by the sun's gravity, an object passing through. On July 2, 2025, the Minor Planet Center made it official. Designation: 3I/Atlas. The 3I marking it as the 3rd confirmed interstellar object in human history, the 3rd visitor from the space between stars. Only 2 had come before: Oumuamua in 2017, that strange elongated object that tumbled through the inner solar system and sparked years of debate about its nature; 2I Borisov in 2019, a more conventional comet that behaved exactly as theory predicted. 3I/Atlas would prove to be neither conventional nor easily explained. The comet was moving at 61 kilometers per second relative to the Sun. For perspective, that's 219,600 kilometers per hour. fast enough to cross the distance between Earth and the Moon in roughly 1 hour and 40 minutes. Voyager 1, humanity's most distant spacecraft, traveling at 17 kilometers per second, moves at barely a quarter of that speed. By the time 3I/Atlas received its official designation, the Minor Planet Center had collected 122 observations from 31 different observatories. The global astronomical community had mobilized with unusual speed. NASA's announcement followed on July 3rd, measured, reassuring. The comet posed no threat to Earth. Its closest approach would occur in mid-December 2025 at a distance of 1.8 astronomical units, approximately 270 million kilometers away, almost twice the distance between Earth and the Sun. Safe, harmless, nothing to fear.
The trajectory was clear. Perihelion, the closest point to the Sun, would occur on October 29, 2025, at roughly 1.4 astronomical units, just beyond Mars's orbit. From there, the comet would swing past Jupiter in March 2026 before continuing its journey back into interstellar space. A tourist, not a threat. Yet within weeks, something shifted. Not in the comet's trajectory, which remained mathematically certain, but in the response. Instruments that normally observed distant galaxies pivoted to focus on this single object. The Hubble Space Telescope captured detailed images on July 21, 2025, when the comet sat 277 million miles from Earth. The James Webb Space Telescope, humanity's most powerful infrared observatory, dedicated observation time to spectroscopic analysis. SPR-ERX, NASA's space telescope designed to map the sky in infrared wavelengths, added 3I by ATLS to its target list. NASA's Mars-orbiting spacecraft prepared for observations as the comet passed within 17 million miles of Mars on October 3rd. The Europa Clipper, en route to Jupiter, adjusted its schedule to potentially observe the comet as it passed behind the Sun from Earth's perspective. This wasn't standard operating procedure for a distant, harmless comet. This was the kind of coordinated mobilization reserved for objects that matter. Objects that require answers. By mid-October, the International Asteroid Warning Network made an announcement that sent quiet ripples through the planetary defense community. They were launching a systematic observation campaign for 3I by ATLS. The first time an interstellar object had been included in a planetary defense-type monitoring drive. The campaign had a name: the 3I by ATLS Comet Astrometry Campaign. It had a timeline: continuous observation from late October through January 2026. It had a goal: maintain round-the-clock tracking from observatories across 6 continents. NASA confirmed participation. So did the European Space Agency. International cooperation at a scale typically reserved for potential impactors. But 3I by ATLS couldn't impact anything. The math was absolute. The danger was zero. So why were they watching it like it might?
Comets are supposed to be predictable. Humanity has studied them for millennia. We've sent spacecraft to rendezvous with them, even landed on their surfaces. The physics of how frozen volatiles sublimate under solar heating is well understood. Water ice dominates, dust lifts away, tails form. The process follows laws written in equations that rarely fail. 3I Atlas doesn't follow those laws. The first sign appeared in early August when NASA's James Webb Space Telescope turned its infrared instruments toward the approaching visitor. JWST specializes in detecting molecules through spectroscopy, breaking light into component wavelengths to identify chemical signatures. Each molecule absorbs and emits light at specific frequencies, leaving fingerprints that reveal composition. What JWST found was unprecedented. The comet's coma, that cloud of gas surrounding the nucleus, contained carbon dioxide at concentrations that defied standard models. The measurements showed a CO2 to H2O ratio of approximately 8:1, 8 parts carbon dioxide for every 1 part water. That's not how comets are built. Most comets in our solar system show water dominance. Jupiter family comets, those with orbits controlled by the giant planet's gravity, typically have carbon dioxide to water ratios closer to 1:1. Long-period comets from the distant Oort cloud, those icy relics that take thousands of years to complete a single orbit, show slightly higher carbon dioxide content, but nothing approaching what 3I Atlas displayed. An 8:1 ratio suggests the object formed in an environment profoundly different from anywhere in our solar system. Perhaps in the outer regions of a protoplanetary disk around a different star, where temperatures allowed carbon dioxide ice to dominate while water remained scarce. Or in a molecular cloud with unusual chemistry, enriched in carbon compounds from previous stellar generations. Or perhaps in conditions we haven't yet imagined. By August 6, 2025, when JWST captured detailed near-infrared spectra, the comet was emitting 129 kilograms of carbon dioxide every second. Simultaneously, only 6.6 kilograms of water. Additionally, 14 kilograms of carbon monoxide and nearly half a kilogram of carbonyl sulfide. The spectroscopic data revealed something else unexpected. Heavy carbon dioxide containing the isotope carbon-13 appeared in the emission lines. Carbon-13 forms in stellar nucleosynthesis, created when stars fuse lighter elements into heavier ones. Its presence and abundance can reveal where and when an object formed. But dust and other gases partially obscured the measurements, making it difficult to quantify exactly how much carbon-13 existed relative to the more common carbon-12. The question remained unanswered, but troubling. NASA's SPREX Space Observatory, designed to map the entire sky in infrared wavelengths, confirmed JWST's findings. SPREX detected an extended carbon dioxide coma stretching at least 348,000 kilometers from the nucleus. That's nearly the distance between Earth and the Moon. A bubble of gas expanding into the vacuum, driven by processes that shouldn't be this active at such distances from the Sun. SPREX lacked the sensitivity to detect water vapor or carbon monoxide at those distances, but the carbon dioxide signal blazed bright and unmistakable. The size of the nucleus itself remained uncertain in ways that felt deliberate, as though the comet was resisting measurement. Hubble's Space Telescope observations from July 21, 2025 suggested the solid core measured somewhere between 0.32 and 5.6 kilometers in diameter. The most likely estimate placed it under 1 kilometer across. That's a massive uncertainty range, the difference between a small mountain and a modest city. And the reason for that uncertainty was the coma itself, the shroud of gas and dust that made direct observation of the nucleus nearly impossible. Astronomers were trying to measure a dark, irregular rock wrapped in a glowing fog, millions of kilometers away, moving at speeds that made long-exposure imaging challenging. But still the error bars felt wider than they should have been, given the resources being deployed.
Reflectance spectra added another layer of strangeness. Data from the Southern African Large Telescope and the Nordic Optical Telescope showed slight reddening in optical wavelengths between 0.4 and 0.7 micrometers, a spectral slope of 22.8% per micrometer. That reddening suggests organic-rich materials, complex carbon compounds similar to those found in comets from the outer reaches of our solar system. But 3I Atlas came from beyond our solar system entirely. The similarity raises questions about whether comet formation processes are universal or whether interstellar objects can mimic local compositions through convergent chemistry. Dust production estimates ranged from 0.3 to 4.2 kilograms per second during the July observation period. That level of activity matched weakly active distant comets in our solar system, more active than expected for an interstellar visitor, but not wildly beyond known parameters. What puzzled observers was the absence of a visible tail. Despite increasing dust production, no tail appeared during the observation window. The coma remained asymmetric, elongated in the anti-solar direction, but no extended structure developed. Viewing geometry could explain part of that.
If Earth's position relative to the comet's trajectory made tail formation difficult to observe, the absence might be an observational artifact. But the lack of fragmentation or rapid changes suggested the nucleus was relatively stable. Large dust grains, less affected by solar radiation pressure, would remain close to the nucleus rather than streaming away into space. Still, comets approaching perihelion typically develop tails. The fact that 3I Atlas resisted doing so felt deliberate. By September, the James Clerk Maxwell telescope detected hydrogen cyanide production. On September 7th, the rate measured 1.5 trillion molecules per second, roughly 2 kilograms. A week later, the rate had tripled to 4.5 trillion molecules per second. The cyanide coma on September 15th stretched 180,000 kilometers across, asymmetric, elongated away from the Sun. A dust tail finally became visible, measuring 50 arc-seconds, approximately 100,000 kilometers. The comet's apparent magnitude had brightened to 14.2, still far too faint for amateur telescopes or binoculars, visible only to professional observatories with sensitive instruments. As October approached and 3I Atlas neared perihelion, activity continued to intensify in ways that matched predictions but with details that remained troubling. The high carbon dioxide ratio, the nickel without iron, the early water outgassing, the carbon chain depletion. Each anomaly had potential natural explanations, but together they formed a pattern that resisted easy categorization. Comets from other star systems should be different from those in our solar system. Different formation environments should produce different compositions. The fact that 3I Atlas shared some similarities with local comets while diverging in critical ways suggested either convergent chemistry across stellar systems or processes we haven't yet identified. Or it suggested the object was something more than a comet. Dr. Avi Loeb, the Harvard astronomer who had argued that Oumuamua might be artificial, renewed his call for rigorous observation and open-minded analysis. He didn't claim 3I Atlas was a spacecraft. He simply argued that dismissing non-natural explanations before gathering all possible data represented intellectual dishonesty. The scientific method requires considering all hypotheses consistent with observations, then eliminating those contradicted by evidence. If observations are ambiguous, if anomalies persist, then ruling out possibilities prematurely prevents discovery. Whether 3I Atlas was a comet with unusual chemistry or something deliberately constructed, the answer would only come from continued observation. And that's exactly what planetary defense systems were quietly organizing. Not because the object posed kinetic danger, the trajectory was clear, the distance was safe, but because something about this visitor demanded answers that routine science alone might not provide.
October 15, 2025, the International Asteroid Warning Network issued a bulletin that most people would scroll past without a second thought. Scientific opportunity, they called it. A chance to refine observation techniques. But those who understood planetary defense protocols recognized something different. This was mobilization. The campaign had a formal designation, the 3I Atlas Comet Astrometry Campaign. The timeline stretched from late October 2025 through January 2026, 2 full months of coordinated observation involving observatories across 6 continents. The stated goal appeared straightforward: maintain continuous tracking of the interstellar visitor, to refine orbital parameters and gather spectroscopic data. Astrometry means measuring where something is in the sky with extreme precision. You take multiple observations from different locations, calculate the orbit, refine the trajectory. Standard procedure for tracking near-Earth objects. What wasn't standard was the scale. The International Asteroid Warning Network exists for one purpose: detecting, tracking, and coordinating responses to objects that might actually hit us. Asteroids on collision courses, comets with uncertain trajectories, things that could vaporize cities or trigger global climate disruption. IWAN doesn't typically organize campaigns for objects passing safely in deep space. They've conducted exercises before, practice runs to test coordination frameworks, but those were announced as drills. This campaign was being framed as scientific observation, yet it had all the operational signatures of emergency response. Universities received participation requests, government observatories adjusted schedules, amateur astronomy networks were asked to contribute data. Registration opened weeks in advance. A workshop was scheduled for late November, location undisclosed to the public. This was the infrastructure you activate when you need answers fast, and you need them verified by as many independent sources as possible, when you can't afford to be wrong. NASA's official statement arrived approximately 6 hours after the IWAN bulletin. 4 words repeated in every press conference, every media interview, every official channel: no threat to Earth. Dr. Lindley Johnson, NASA's planetary defense officer, went on record confirming the comet would pass at approximately 1.8 astronomical units from Earth. That's about 270 million kilometers. For perspective, the Moon sits only 384,000 kilometers away. By cosmic standards, I-3 Atlas wasn't even in our neighborhood. Safe distance, clear trajectory, zero impact probability. And yet,
reports began circulating through outlets with sources inside aerospace and defense sectors. Defense satellites had been retasked, not announced publicly, not included in routine mission updates. But individuals who worked adjacent to these systems noticed the changes. Classified observation platforms operated by the United States Space Force and partner agencies shifted their coverage windows. Deep space infrared sensors, assets normally monitoring geosynchronous orbits or tracking foreign satellites, pivoted to focus on a comet that officially posed no risk. High-gain radar arrays, capable of detecting objects millions of kilometers away, adjusted pointing protocols. One source, speaking under conditions of anonymity to multiple news organizations, described it as precautionary reorientation. Another called it protocol compliance. A third used language more direct. It reminded them of the scramble before the 2008 TC-3 impact, when agencies had 19 hours to confirm an asteroid was going to hit Sudan. Except this time there was no impact, no countdown, no threat. So what were they preparing for? The Deep Space Network, NASA's array of massive radio dishes used to communicate with distant spacecraft, dedicated observation windows to radar tracking of 3I ATLS. DSN time is precious. It's scheduled months in advance. Mission controllers compete for access. Clearing time requires justification. Someone had to decide that focusing on this comet was more valuable than maintaining communications with active spacecraft or conducting planned observations of other targets. Radar provides data that optical telescopes cannot: rotation rates, surface roughness, precise distance measurements, the shape and structure of objects shrouded in dust. You don't use radar unless the data is critical. NASA's spacecraft orbiting Mars prepared for observations as 3I ATLS passed within 17 million miles of the Red Planet on October 3, 2025. The ExoMars Trace Gas Orbiter, operated jointly by the European Space Agency and Russia's Roscosmos, used its color and stereo surface imaging system to capture images of the comet's coma. That instrument normally photographs Mars's surface. Imaging a comet 50,000 times fainter than typical targets required 5-second exposures and careful planning. Mission time dedicated to an object that couldn't hurt the spacecraft or its science objectives, but someone decided it was worth doing anyway. The Europa Clipper, NASA's spacecraft en route to Jupiter's icy moon, adjusted its observation schedule. The probe was scheduled to pass behind the Sun from Earth's perspective during solar conjunction in late October, precisely when 3I ATLS would be near perihelion. Solar conjunction makes communication difficult. The Sun's radio noise drowns out signals. Spacecraft typically enter safe mode during these periods, waiting for clearer conditions before resuming full operations.
Europa Clipper's team planned to use that downtime to observe 3I ATLS if the geometry allowed. Not a mission priority, not related to the probe's Jupiter objectives, but an opportunity deemed valuable enough to plan for. The James Webb Telescope, humanity's most powerful infrared observatory and one of the most oversubscribed scientific instruments ever built, dedicated multiple observation windows to 3I ATLS throughout August and September. JWST time is allocated through competitive peer review. Proposals are submitted months or years in advance. Approved projects get scheduled with precision measured in minutes. Observing a distant comet requires justification that passes scrutiny from the global astronomical community. The fact that multiple JWST observation sessions focused on 3I ATLS indicates the science case was compelling enough to override other priorities, or that priorities had shifted for reasons not entirely scientific. The Hubble Space Telescope captured detailed images on July 21, 2025, when the comet was 277 million miles from Earth. SPHRX, NASA's infrared space telescope designed to map the entire sky, added 3I ATLS to its target list despite the comet not fitting standard survey parameters. Ground-based observatories joined the effort. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the James Clerk Maxwell Telescope, the Southern African Large Telescope, the Nordic Optical Telescope, the Zwicky Transient Facility, Canada-France-Hawaii Telescope, Lowell Discovery Telescope.
Professional facilities and amateur networks all contributing data to centralized databases managed by the Minor Planet Center and shared with planetary defense coordination offices worldwide. This level of coordination doesn't happen spontaneously. It requires planning, communication protocols, data sharing agreements, institutional buy-in from organizations that normally operate independently. Apophis, the asteroid that caused concern in 2004 because of a 1 in 45,000 chance of impacting Earth in 2029, received this level of attention. The global astronomical community mobilized, observations accumulated, the uncertainty narrowed. Eventually, the danger was ruled out. That campaign set the standard for how humanity responds to potential threats. The 3I Atlas campaign had that same intensity, that same urgency, except there was no impact uncertainty. The trajectory was clear, the distance was safe. So what were they narrowing in on? Media outlets, particularly those with defense and aerospace sources, reported rumblings of something called anomaly detection readiness. Not a formal term found in any NASA document, but people who work adjacent to planetary defense systems started using it in private conversations. The concept, as best as anyone could piece together, suggested modern defense postures aren't just about impacts anymore. They're about detecting things that don't fit, objects that behave unexpectedly, signals that shouldn't be there. A shift from kinetic defense to informational defense, less about stopping rocks, more about understanding what we're looking at before it's too late to respond appropriately. 3 interstellar objects detected in less than a decade. Before 2017, we'd never confirmed a single one. Now we were averaging nearly one every 3 years. Each one strange in its own way, each one raising questions we didn't have frameworks to answer. And each time, the gap between public reassurance and private concern seemed to widen. Perhaps agencies learned something from Oumuamua and 2I Borisov. Perhaps they decided that no threat and fully understood aren't the same thing. Perhaps they were preparing for the possibility that this object, like those before it, was more than it appeared. The New York Post ran an article in mid-October with a headline using the phrase, "Interplanetary Defense System Deployed." The article cited unnamed NASA sources and suggested protocols normally reserved for potential impactors were being quietly activated.
It mentioned NEWISE, the infrared space telescope that surveys for asteroids, being tasked with additional observations. It referenced data-sharing agreements between NASA and the Department of Defense that allow certain telescopic assets to be reprioritized under national security justifications. It even mentioned a protocol designation, IPD-9, allegedly governing responses to anomalous deep space objects. No public documents reference IPD-9. No official confirmation exists, but multiple independent sources used the same designation, either a coordinated leak or a shared misunderstanding of something real. By late October, as 3I Atlas approached perihelion, the operational tempo increased. Observation requests intensified. Data submission protocols became more formalized, with emphasis on calibration standards and error reporting. This wasn't casual scientific interest. This was institutional-grade coordination, the kind you implement when data matters, when decisions might hinge on the quality of observations, when you can't afford gaps or inconsistencies. So here was the paradox: an object that couldn't hurt us being watched like it might, a campaign framed as science, structured like defense, statements assuring safety while actions suggested preparation for something unspoken. At the center of it all, 3I Atlas continued its journey, hurtling through the inner solar system at 61 kilometers per second, emitting gases we didn't expect, following a trajectory that felt too precise to be random. And somewhere in classified briefing rooms and secure communication channels, decisions were being made about what to look for, what to prioritize, and perhaps what to prepare for if those anomalies didn't resolve into something comfortable. The campaign would run through January. The data would eventually be published. The workshop would produce findings. But by then, the comet would be gone, fading into the darkness beyond our detection range. And the questions we should have asked would be harder to answer.
There's a language that institutions use when they want to reassure without revealing. Careful calibration of words designed to inform without alarming, to acknowledge without admitting. NASA's public communications around 3I Atlas are textbook examples of this precision. Every press release, every interview, every official statement echoes the same core message: no threat to Earth. And technically, that statement is absolutely correct. The object will not impact our planet. Its trajectory is well understood. The mathematical certainty of its safe passage is beyond question. But notice what's not being said. No mention of threat to satellites, no mention of effects on spacecraft, no discussion of radiation, electromagnetic interference, or any non-kinetic hazards. The assurance is narrow, specific, and precisely worded. It tells you what won't happen, not what might. The European Space Agency followed a similar pattern. They emphasized the scientific value of studying an interstellar visitor, the rarity of the opportunity, the importance of international cooperation. All true, all uncontroversial. But ESA's Mars Express orbiter, which was scheduled to conduct observations of Martian surface features in late October, had its observation plan adjusted to include imaging attempts of 3I Atlas during its closest approach to Mars orbital space. That adjustment wasn't announced publicly until after it happened. Why the discretion? If this is purely scientific opportunity, why not celebrate it? Why not highlight the flexibility and responsiveness of interplanetary missions? The silence suggests someone decided that less public attention was preferable to more. The Minor Planet Center, the organization responsible for cataloging small bodies in the solar system, has been updating orbital elements for 3I Atlas regularly. Their data is public, available to anyone with an internet connection, standard transparency. But the error bars on certain parameters, particularly non-gravitational acceleration terms, have been fluctuating more than usual. Non-gravitational acceleration refers to forces other than gravity affecting an object's trajectory. usually outgassing from comets as they release jets of gas. You can model it, predict it, correct for it. But with 3I AT-Atlas, those corrections keep changing. Each new batch of observations requires tweaking the model. That's not shocking for active comets, but the magnitude and inconsistency are raising quiet concerns among professionals who track these things. Some researchers have noted privately that the object's brightness curve, how much light it reflects over time, doesn't match standard sublimation models. It's irregular, almost pulsed, as if outgassing is happening in bursts rather than steadily. That behavior could be natural, driven by rotation or localized active regions on the nucleus. Or it could indicate something more controlled, more deliberate. The timing between observation, analysis, and public disclosure reveals patterns worth noting. JWST captured its spectroscopic data of 3I AT-Atlas in late August. That data showed the unusual carbon dioxide dominance discussed earlier. But the findings weren't released publicly until mid-September, roughly 3 weeks later. Peer review takes time. Data needs to be verified, calibrated, interpreted. But JWST observations of other comets have been shared more quickly, sometimes within days, especially when findings are exciting. Why the delay? Caution? Thoroughness? Or something else? A review process that extended beyond usual scientific channels, perhaps into security or policy discussions about how to frame the findings. Data embargoes are standard in astronomy. When a major observatory captures unique data, the team that proposed the observations typically gets exclusive access for a period, often 6 months to a year, to analyze and publish findings before releasing raw data publicly. That's fair. It protects the intellectual investment of researchers, but it also creates opacity. We know JWST looked at 3I AT-Atlas. We know ground-based telescopes have been tracking it. We know radar facilities attempted observations. But we don't know everything those instruments have seen. We don't know what's sitting in embargoed data archives, awaiting publication or clearance or some other form of approval before reaching public consciousness. In a situation where public interest is high and official statements are carefully limited, that opacity fuels questions. Consider the phrasing again, no threat to Earth. Why specify Earth? Why not say no threat to anyone, or no threat detected, or no danger? The specificity implies someone asked or someone worried about threats that aren't planetary scale. Threats to infrastructure, perhaps. The increasing reliance on satellite constellations for communications, GPS, internet, military coordination creates vulnerabilities. A large solar storm can disrupt those systems. So can intense cosmic radiation. Could an object like 3I Atlas, with its unusual emissions and high-energy environment, pose a risk to orbital assets without threatening the planet itself? That's a question that wouldn't have been relevant 30 years ago, but today, with tens of thousands of satellites planned for low Earth orbit, it's suddenly very pertinent. If agencies are quietly assessing that risk, they might frame public statements to avoid panic without lying about the specific danger being evaluated. There's also the regulatory environment to consider. In the United States, certain types of astronomical data can fall under export control if they have potential national security implications. The International Traffic in Arms Regulations, known as ITAR, governs what information can be shared internationally. If observations of 3I Atlas revealed something, anything that defense analysts deemed sensitive, not because it's dangerous but because it's informative about detection capabilities or analysis methods, that data could be classified or restricted. It doesn't require conspiracy. It just requires bureaucrats following rules designed to protect strategic advantages. The result, though, is the same. A gap between what professionals know and what the public is told. A gap that grows larger the more unusual the object becomes. Past precedent offers guidance. After Oumuamua's discovery in 2017, the SETI Institute coordinated radio observations to check for artificial signals. None were found. But the fact that those observations happened, that someone decided they were worth doing, indicates a protocol exists for treating interstellar objects as potential technosignature candidates.
If that protocol is being applied to 3I Atlas, we might not know. SETI observations can be conducted privately, with findings only disclosed if something unambiguous is detected. Silence in that context doesn't mean nothing was looked for. It means nothing was found or nothing conclusive enough to announce. Dr. Avi Loeb, the Harvard astrophysicist who gained prominence for suggesting Oumuamua might be artificial, has been vocal about 3I Atlas. He's not claiming the comet is a spacecraft. He's saying we should keep that possibility on the table, run observations that could rule it out or support it, and not dismiss the idea reflexively because it makes us uncomfortable. During an appearance on Elizabeth Vargas Reports, Loeb emphasized the unusual characteristics. The massive size, potentially 33 billion tons based on Webb telescope observations. The fact that it's at least 1,000 times more massive than previous interstellar objects. This, he stated, raises the question, why is such a colossal entity entering our inner solar system when we have only observed smaller ones in the past? He likened the comet's arrival to a blind date. You presume your date will be pleasant, but you also have to consider the possibility of encountering dangerous individuals. Loeb urged the global community to remain alert and develop a defensive strategy in case 3I Atlas turns out to be a black swan event, a rare high-impact occurrence that's hard to predict but seems obvious in retrospect. He noted the anti-tail, a stream of particles directed toward the sun instead of away from it, contrary to expected behavior. The nickel emissions without iron, the non-gravitational acceleration, the unusual path bringing it close to Jupiter, Venus, and Mars. In a paper published in July, Loeb suggested these elements might indicate an alien probe sent for reconnaissance, potentially with hostile motives. The hypothesis stated that if 3I Atlas is a technological artifact with active intelligence, two scenarios could arise, one where its intentions are entirely benevolent, another where they're malevolent. Whether you agree with Loeb or not, his point about intellectual honesty is difficult to dismiss. If we only look for what we expect to find, we'll miss what's actually there. NASA officially maintains that 3I Atlas poses no threat. The International Asteroid Warning Network confirms participation in the observation campaign, but frames it as standard methodology refinement. Yet the campaign timeline, November 27, 2025 through January 27, 2026, represents the first time an interstellar object has been included in a planetary defense-type monitoring drive. The pattern repeats. Official statements that are technically accurate but narrowly scoped, observational data that's embargoed or delayed, coordination that happens behind closed doors, revealed only through leaks or inconsistencies.
The specificity implies someone asked or someone worried about threats that aren't planetary scale. Threats to infrastructure, perhaps. The increasing reliance on satellite constellations for communications, GPS, internet, military coordination creates vulnerabilities. A large solar storm can disrupt those systems. So can intense cosmic radiation. Could an object like 3I Atlas, with its unusual emissions and high-energy environment, pose a risk to orbital assets without threatening the planet itself? That's a question that wouldn't have been relevant 30 years ago. But today, with tens of thousands of satellites planned for low Earth orbit, it's suddenly very pertinent. If agencies are quietly assessing that risk, they might frame public statements to avoid panic without lying about the specific danger being evaluated. There's also the regulatory environment to consider. In the United States, certain types of astronomical data can fall under export control if they have potential national security implications. The International Traffic in Arms Regulations, known as ITAR, governs what information can be shared internationally. If observations of 3I Atlas revealed something, anything that defense analysts deem sensitive, not because it's dangerous, but because it's informative about detection capabilities or analysis methods, that data could be classified or restricted. It doesn't require conspiracy. It just requires bureaucrats following rules designed to protect strategic advantages. The result, though, is the same: a gap between what professionals know and what the public is told, a gap that grows larger the more unusual the object becomes. Past precedent offers guidance. After Oumuamua's discovery in 2017, The SETI Institute coordinated radio observations to check for artificial signals. None were found. But the fact that those observations happened, that someone decided they were worth doing, indicates a protocol exists for treating interstellar objects as potential technosignature candidates. If that protocol is being applied to 3I Atlas, we might not know. SETI observations can be conducted privately, with findings only disclosed if something unambiguous is detected. Silence in that context doesn't mean nothing was looked for. It means nothing was found, or nothing conclusive enough to announce. Dr. Avi Loeb, the Harvard astrophysicist who gained prominence for suggesting Oumuamua might be artificial, has been vocal about 3I Atlas. He's not claiming the comet is a spacecraft. He's saying we should keep that possibility on the table, run observations that could rule it out or support it, and not dismiss the idea reflexively because it makes us uncomfortable. During an appearance on Elizabeth Vargas Reports, Loeb emphasized the unusual characteristics: the massive size, potentially 33 billion tons based on Webb telescope observations, the fact that it's at least 1,000 times more massive than previous interstellar objects. He stated, "This raises the question, why is such a colossal entity entering our inner solar system when we have only observed smaller ones in the past?" He likened the comet's arrival to a blind date. You presume your date will be pleasant, but you also have to consider the possibility of encountering dangerous individuals. Loeb urged the global community to remain alert and develop a defensive strategy in case 3I Atlas turns out to be a black swan event, a rare, high-impact occurrence that's hard to predict but seems obvious in retrospect. He noted the antitail, a stream of particles directed toward the sun instead of away from it, contrary to expected behavior. The nickel emissions without iron, the non-gravitational acceleration, the unusual path bringing it close to Jupiter, Venus, and Mars. In the paper published in July, Loeb suggested these elements might indicate an alien probe sent for reconnaissance, potentially with hostile motives. The hypothesis stated that if 3I Atlas is a technological artifact with active intelligence, two scenarios could arise: one where its intentions are entirely benevolent, another where they're malevolent. Whether you agree with Loeb or not, his point about intellectual honesty is difficult to dismiss. If we only look for what we expect to find, we'll miss what's actually there. NASA officially maintains that 3I Atlas poses no threat. The International Asteroid Warning Network confirms participation in the observation campaign, but frames it as standard methodology refinement. Yet the campaign timeline, November 27, 2025 through January 27, 2026, represents the first time an interstellar object has been included in a planetary defense-type monitoring drive. The pattern repeats: official statements that are technically accurate, but narrowly scoped; observational data that's embargoed or delayed; coordination that happens behind closed doors, revealed only through leaks or inconsistencies. It's not quite a cover-up, because there's no clear evidence of deception, but it's not quite transparency either. It's something in between, a managed narrative, where institutions controlling information decide what the public needs to know and when they need to know it. Perhaps that's appropriate. Perhaps there are good reasons to move slowly, to verify findings before broadcasting them, to avoid causing unnecessary alarm over anomalies that might resolve into mundane explanations. But the cost of that caution is trust. Every delay, every vague statement, every unanswered question feeds the perception that something is being withheld. And in an era where institutional trust is already fragile, that perception becomes its own kind of crisis, separate from whatever the object itself might represent. So here we are, caught between two realities: the official one, where 3I/Atlas is a fascinating but harmless comet being studied by cooperative international teams, and the unofficial one, where defense systems are quietly engaged, data is carefully controlled, and the full story won't be told until long after the object has left our vicinity. Which reality is more accurate? Probably both. Probably neither. Probably something in the uncomfortable space between them,
where facts and fears coexist, and the line separating science from security blurs beyond recognition.
October 19, 2017. Astronomers at the University of Hawaii's Pan-STARRS telescope review images from the previous night's survey and notice something odd. A faint streak, moving fast, already past Earth, heading out of the solar system. Follow-up observations over the next few weeks confirm what seems impossible. The object came from interstellar space, passed within 24 million kilometers of Earth, and is now leaving, never to return. They name it Oumuamua, Hawaiian for scout or messenger, and the world's first confirmed interstellar visitor becomes an instant sensation. But Oumuamua doesn't behave. Its shape, inferred from brightness variations, is extremely elongated, possibly 10 times longer than it is wide. It shows no signs of cometary activity, no tail, no coma, despite passing close to the Sun where ices should vaporize. And then, as it recedes, astronomers detect a slight acceleration, a deviation from the trajectory gravity alone would produce. Comets do this all the time through outgassing, but Oumuamua showed no outgassing. So what pushed it? Explanations proliferated. Maybe it's outgassing hydrogen, which would be invisible. Maybe it's a fragment of a planet shattered by tidal forces and flung into space. Maybe it's a nitrogen iceberg from a Pluto-like world. Or maybe, as Dr. Avi Loeb proposed, it's a light sail, a piece of technology designed to be pushed by starlight, sent by some distant civilization. The scientific community largely dismissed the artificial hypothesis, not because it was impossible, but because natural explanations, however contrived, felt safer. The burden of proof for claiming alien technology is extraordinarily high. Extraordinary claims require extraordinary evidence. By the time serious debate emerged, Oumuamua had already faded from view. Too far, too faint, too fast. The questions remained unanswered. August 30, 2019. Gennady Borisov, an amateur astronomer at the Margot Observatory in Crimea, discovers another interstellar visitor. This one behaves exactly as comets should behave. Designated 2I Borisov, the object displays a clear coma and tail. Spectroscopic observations show water vapor, carbon monoxide, and cyanide emissions consistent with comets from our own solar system. Its composition suggests it formed in conditions similar to those in the outer regions of our planetary system. 2I Borisov was reassuring. It confirmed that interstellar comets exist and that they can be ordinary. Not every visitor from beyond needs to be strange. But that reassurance was temporary. July 1, 2025. A telescope in Chile detects movement. Not an asteroid, not a satellite. Something traveling at 61 kilometers per second from a direction no object should be coming from. 3I Atlas. The third confirmed interstellar object, and from the beginning it was clear this one would be different. Oumuamua raised questions about acceleration without outgassing. 2I Borisov answered questions about whether interstellar comets could be normal. 3I Atlas brings both mysteries together and adds new ones. It has a coma like 2I Borisov. It shows cometary activity. But the composition is wrong. The carbon dioxide dominance, the nickel emissions without iron, the early water outgassing, the carbon chain depletion. It doesn't accelerate mysteriously like Oumuamua. Its non-gravitational forces match expectations for an active comet, but those forces fluctuate in ways that resist easy modeling. It came from interstellar space like both predecessors, but its trajectory brought it unusually close to the ecliptic plane, the flat disk where planets orbit. The odds of that alignment aren't zero, but they're low enough to notice. 3 visitors in 8 years, each one strange in its own way. Each one pushing the boundaries of what we thought we understood about objects from beyond our solar system. The pattern suggests either we've been extraordinarily lucky to catch these rare travelers, or interstellar objects are far more common than models predicted, and we're only now developing the technology to detect them. The Atlas survey network that discovered 3I Atlas became operational in 2015. Pan-STARRS, which found Oumuamua, began full operations in 2010.
The Virasi-Rubin Observatory, which serendipitously imaged 3I Atlas during science validation, hasn't even started its full sky survey yet. Our detection capabilities have increased dramatically in the last decade. As those capabilities continue improving, we should expect more interstellar visitors. The question is what we'll find when we look more closely. After Oumuamua, protocols began forming. Not official policies written in government documents, but institutional memory. Lessons learned about how to respond when something doesn't fit existing categories. The SETI Institute coordinated radio observations of Oumuamua to search for artificial signals. They found nothing. But the fact that the search happened established precedent. Interstellar objects would be treated as potential technosignature candidates until proven otherwise. When 2I Borisov appeared, those protocols activated more smoothly. Observations were coordinated quickly, spectroscopic data accumulated efficiently. The object was characterized thoroughly before it left the inner solar system.
By the time 3I ATLS was discovered, the response framework had matured. The International Asteroid Warning Network didn't wait for anomalies to emerge. They preemptively launched a systematic observation campaign. That represents evolution, a shift from reactive to proactive, from scientific curiosity to something closer to reconnaissance. The 3I ATLS Comet Astronomy Campaign, running from November 27, 2025 through January 27, 2026, is described as an opportunity to introduce IWAN's methodology to new and seasoned observers, a chance to refine coordination frameworks. But it's also the first time an interstellar object has been integrated into planetary defense infrastructure as if it were a near-Earth object requiring continuous monitoring. That's not how we treated Oumuamua. That's not how we treated 2I Borisov. Something changed. Perhaps agencies recognized that interstellar objects represent a category we hadn't adequately prepared for. Not threats in the traditional sense of impact risk, but unknowns that require different evaluation frameworks. Perhaps the anomalies in Oumuamua and 3I ATLS suggested natural explanations aren't always sufficient. Or perhaps, after 3 visitors in 8 years, someone decided we need to know more about what's passing through our cosmic neighborhood and why these objects keep arriving with characteristics that defy easy categorization. Dr. Loeb's warnings about 3I ATLS being a potential black swan event echo concerns raised after Oumuamua. Black swan events are rare, high-impact occurrences that seem obvious in retrospect but are nearly impossible to predict beforehand. The term comes from the discovery that black swans exist in Australia, overturning the European assumption that all swans are white. It represents paradigm-shifting revelations that challenge fundamental assumptions. If Oumuamua was artificial, that would have been a black swan. We would have learned we're not alone in a universe we assumed was empty of technological civilizations within observable range. If 3I ATLS is artificial, or if it represents something we haven't even conceived of yet, that becomes another black swan, another fundamental assumption overturned. The pattern repeats. Objects that don't quite fit, responses that seem disproportionate to stated risks, gaps between what we're told and what actions suggest. Each interstellar visitor has taught us something. Oumuamua taught us that objects can pass through our solar system without being captured by the sun's gravity, that their shapes and behaviors might not match our models. 2I Borisov taught us that some interstellar visitors are exactly what we expect, that not every mystery requires exotic explanations. 3I ATLS is teaching us that the story isn't over, that each new visitor brings new questions, and that our frameworks for understanding what arrives from beyond might need to expand beyond natural versus artificial into categories we haven't yet defined. The jet observed on August 2, 2025, pointed toward the sun. That's normal behavior for comets. As the nucleus warms, volatile ices sublimate and create directed outflows. But the intensity caught attention. The 2-meter twin telescope at Teide Observatory captured 159 exposures of 50 seconds each to create the composite image. The jet appeared as a purple stream blasting from the nucleus toward our star.
Astronomers were notified via the Astronomer's Telegram on October 15th. Not unusual, that announcement service exists for the astronomy community to share time-sensitive observations. What was unusual was the emphasis. The language suggesting this wasn't just routine cometary activity, but something requiring immediate attention from the global community. As 3I ATLS approached perihelion on October 29, 2025, it passed behind the Sun from Earth's perspective. Solar conjunction occurred on October 21st. For 8 days around perihelion, the comet couldn't be observed from Earth. That timing meant the period of maximum activity, when the comet was closest to the Sun and most energetic, happened while we couldn't watch directly. Mars orbiters filled that gap. The ExoMars Trace Gas Orbiter used its color and stereo surface imaging system to capture images as the comet passed within 17 million miles of the red planet.
GOES-19, a weather satellite, observed the comet between October 18th and 24th, able to detect objects down to magnitude 12. Europa Clipper, en route to Jupiter, planned observations during its own solar conjunction. The spacecraft would potentially be showered with charged particles from the comet's tail. That's an opportunity for science, measuring the composition and density of cometary material directly. But it's also a test. How do spacecraft systems respond to unexpected particle environments? What happens when we pass through the debris field of an object we don't fully understand? By the time 3I Bost Atlas emerges from behind the Sun in November 2025, it will be visible before sunrise, growing dimmer as it moves away. Through December, it will travel through Virgo in Leo, fading below magnitude 12. The observation window is closing. The campaign runs through January 27, 2026. After that, the comet will be too faint, too distant. Whatever answers exist, they need to be found now. Because once 3I Bost Atlas fades into the darkness beyond our detection range, we'll be left with data, questions, and the certainty that another visitor will eventually arrive. And when it does, we'll need to decide whether we're still looking at natural phenomena that happen to be strange, or whether we're seeing something else entirely.
Size matters in astronomy, not just for gravitational influence or collision risk, but for what size reveals about origin and history. 3I Atlas is massive, potentially 33 billion tons based on observations from the James Webb Space Telescope. That makes it at least 1,000 times more massive than previous interstellar objects. Oumuamua measured roughly 400 meters along its longest axis, small enough to fit inside a large sports stadium. 2I Borisov's nucleus was estimated at about 500 meters across, modest by cometary standards. 3I Atlas sits somewhere between 320 meters and 5.6 kilometers in diameter. The upper limit makes it comparable to city-sized objects. The uncertainty comes from the coma obscuring direct observation. But even the lower estimate puts it in a different category from its predecessors. Why is such a colossal entity entering our inner solar system when we have only observed smaller ones in the past? Dr. Loeb asked during his media appearances. It's a reasonable question without a satisfying answer. Perhaps larger interstellar objects are simply harder to detect at great distances. Perhaps we've been lucky to spot the smaller ones and unlucky to have missed larger ones until now. Or perhaps this one is different for reasons that have nothing to do with natural selection bias. The velocity adds to the mystery. 3I Atlas is traveling at 209,000 kilometers per hour, roughly 130,000 miles per hour, the highest velocity ever recorded for a solar system visitor. That speed isn't just momentum from its parent star system. It's the accumulated effect of gravitational interactions over billions of years. Each close pass by a star, each traversal through a molecular cloud added energy. The longer 3I Atlas drifted through interstellar space, the higher its speed grew. No one knows where the comet came from, said David Jewett of UCLA, science team leader for Hubble observations. It's like glimpsing a rifle bullet for 1,000th of a second. You can't project that back with any accuracy to figure out where it started on its path. That's fundamentally different from objects in our solar system. We can trace asteroid orbits back thousands or millions of years with reasonable precision. We know where they've been. We can predict where they're going. 3I Atlas erases that certainty. Its history is unknowable. Its future trajectory after leaving our solar system is calculable,
but meaningless. We'll never know where it ends up. The anti-tail phenomenon caught particular attention. Normal comet tails point away from the sun, pushed by solar radiation and the solar wind. That's basic physics. Light exerts pressure. Charged particles from the sun create outward force. 3II Atlas showed a stream of particles directed toward the sun, an anti-tail. Anti-tails aren't impossible. They occur when viewing geometry creates the illusion of material moving sunward. The particles are still moving away from the sun, but the angle from which we observe makes it appear otherwise. But the intensity and persistence of 3II Atlas's anti-tail suggested something beyond simple optical illusion. The jet captured by the 2-meter twin telescope on August 2nd showed material actively streaming toward the sun, not just appearing to do so. This is normal behavior for comets, experts assured the public. And technically, that's true. Comets emit jets. Those jets can point in various directions, depending on the rotation of the nucleus and the location of active regions. But normal and expected aren't the same thing. The fact that scientists felt the need to emphasize normalcy suggests the observation was unusual enough to warrant explanation. The nickel emissions remain the most puzzling aspect. Atomic nickel venting into space at roughly 4 grams per second without any corresponding iron. Nickel and iron are cosmically inseparable. They form together in stellar cores. They mix in planetary materials. Finding one without the other requires specific processes that don't occur naturally in most environments. Dr. Loeb noted that nickel tetracarbonyl, the compound possibly forming in 3II Atlas, has only been observed in human manufacturing processes. It's used in industrial refining. It's toxic, and finding it in a comet raises uncomfortable questions about how natural this object actually is. Natural explanations exist. Carbonyl chemistry could occur under the right conditions. Primordial materials from different stellar environments might have unusual compositions. Space weathering over billions of years could alter surface chemistry in unexpected ways. But each explanation requires assumptions that stretch existing models. Each requires special circumstances. At some point, the accumulation of special circumstances becomes less convincing than simpler explanations we're hesitant to consider. The trajectory brings 3II Atlas uncomfortably close to multiple planets. Past Mars on October 3rd, near Earth at 1.8 astronomical units in December, swinging past Jupiter in March 2026. Venus will also experience a close approach, though the exact distance varies depending on orbital positions. Its unusual path will bring it uncomfortably close to Jupiter, Venus, and Mars, Loeb observed. Uncomfortable is subjective. The distances are all safe by astronomical standards. But the trajectory's precision, the way it threads between multiple planetary orbits, feels deliberate. Random interstellar objects shouldn't preferentially align with the ecliptic plane. They shouldn't pass close to multiple major bodies in a single flyby. The odds aren't zero, but they're low enough to make pattern-seeking humans notice.
Non-gravitational acceleration adds another variable. Comets routinely experience forces beyond gravity as outgassing creates thrust. That's how Oumuamua's acceleration was eventually explained, though the lack of visible outgassing made that explanation controversial. 3I ATLS shows clear outgassing. Its non-gravitational forces match expectations for an active comet, but the magnitude and direction of those forces keep changing in ways that resist easy modeling. Each new batch of observations requires tweaking the parameters. The error bars on acceleration terms fluctuate more than they should for a simple sublimation-driven process. That could mean the comet's rotation is complex, with multiple active regions turning on and off as they face the sun. It could mean the composition varies across the surface more dramatically than usual. Or it could mean the forces acting on 3I ATLS aren't entirely passive. The timing of solar conjunction matters. The comet reached its closest point to the Sun on October 29th. From October 21st through the end of October, it was positioned on the opposite side of the Sun from Earth, invisible to most telescopes. The period of maximum activity, when heating would be most intense and outgassing most vigorous, happened while we couldn't watch directly. How the comet behaves during this phase can help researchers understand what it is made of and where it came from, media reports noted. But we'll only know what happened based on data from Mars orbiters and other spacecraft positioned to observe during the gap. That creates opportunity for uncertainty. What if something happened during solar conjunction that we missed? What if the object changed in ways we won't detect until it emerges and the damage is already done? These aren't reasonable scientific concerns, they're paranoia dressed in possibility. But paranoia exists because sometimes the unlikely thing actually happens. 3I ATLS differs from its predecessors in almost every measurable way. Larger than Oumuamua, more chemically complex than 2I Borisov, faster than either, more closely monitored than both. And yet, for all the observation, all the data, all the institutional mobilization, the fundamental questions remain unanswered. Is it a comet with unusual chemistry, an ancient relic from a stellar environment unlike anything in our solar system, a natural object that happens to tick multiple boxes for anomalous behavior purely by coincidence? Or is it something we're not prepared to name yet?
Some questions don't get asked in official press conferences. They circulate in private conversations, in emails between colleagues, in the margins of observation proposals. Why is the International Asteroid Warning Network treating an interstellar visitor like a potential impactor when the trajectory is mathematically certain to pass safely? Why did defense satellites retask for an object that NASA repeatedly assures poses no threat? Why the emphasis on continuous observation when previous interstellar objects received interest but not urgency? The official answer is consistent: scientific opportunity, refining observation techniques, testing coordination frameworks, gathering data on a rare visitor from beyond our solar system. All true, all reasonable, and all insufficient to explain the scale of response. SETI observations of Oumuamua were acknowledged publicly after the fact. The Breakthrough Listen project used the Green Bank telescope to search for artificial signals. They found none. But that effort was announced, publicized, framed as responsible due diligence, given the object's unusual characteristics. If similar observations are being conducted for 3I ATLS, we haven't been told. Silence doesn't mean nothing is happening. It means either nothing unusual was detected, or the results aren't ready for public disclosure. The technosignature question sits uncomfortably in scientific discourse. Mainstream astronomers acknowledge the theoretical possibility that artificial objects could traverse interstellar space. The laws of physics don't forbid it. Our own Voyager probes are doing exactly that, though at much slower speeds. But suggesting that any specific object might be artificial invites professional risk. It positions you as a fringe thinker. It damages credibility, even when the suggestion is framed carefully as one hypothesis among many. Dr. Loeb has accepted that stigma. His willingness to publicly discuss the possibility that Oumuamua, or 3I ATLS, might be artificial has made him simultaneously famous and controversial. The paper suggested these elements might indicate it is an alien probe sent for reconnaissance of Earth, potentially with hostile motives, media reports summarized his July publication. Loeb himself frames it more carefully. Not a claim that 3I ATLS is artificial. A suggestion that we should collect data capable of ruling out that hypothesis rather than dismissing it reflexively. If this object is a technological artifact with active intelligence, two scenarios could arise. One where its intentions are entirely benevolent, another where they're malevolent. The latter scenario invokes the Trojan horse analogy, something that appears natural but functions strategically. A reconnaissance asset disguised as a comet gathering data while humanity debates its composition. It's speculative, it's provocative, and it's unfalsifiable without specific types of observations that may or may not be happening. The black swan framing resonates because it captures the essence of paradigm shift. Before Europeans encountered Australia, the existence of black swans was considered impossible. All swans were white. That was established fact. Then they found black swans. The paradigm shifted. What was impossible became mundane.
If 3I ATLS is artificial, or if it represents a category of object we haven't even conceived of yet, that becomes a black swan event for astronomy. Everything we think we know about interstellar space would need reassessment. The probability seems low, but low probability isn't zero probability, and the consequences of being wrong by assuming naturalness when the truth is otherwise could be catastrophic. So the observation campaign continues. The data accumulates, and the questions that should be asked explicitly remain implicit, whispered in conferences, but absent from official documentation.
What specific observations could definitively rule out artificial origin? Are those observations being conducted? If so, by whom? And if results exist, why haven't they been shared? The gap between what professionals suspect and what institutions acknowledge grows wider the longer silence persists. Perhaps there's nothing unusual happening. Perhaps 3I/Atlas will fade into history as an interesting but natural comet from another star system. Perhaps the mobilization was prudent caution that happened to find nothing alarming. But until that conclusion is stated clearly, with supporting data made public, doubt will persist. And doubt, in the absence of transparency, becomes its own kind of crisis.
November 2025. 3I Atlas emerges from behind the sun, visible again before sunrise. Dimmer now, moving away. Through December, it will traverse Virgo and Leo, fading steadily. By January, its apparent magnitude will drop below 12, too faint for most amateur telescopes, accessible only to professional observatories with large apertures and sensitive cameras. The observation campaign runs through January 27, 2026. After that date, coordinated tracking will cease. Individual observatories might continue monitoring as long as detection remains possible, but the systematic round-the-clock coverage will end. The window is closing. Whatever answers exist in the data collected over these months will need to be extracted, analyzed, peer-reviewed, and published. That process takes time, months at minimum, more likely years before comprehensive understanding emerges. By then, 3I Atlas will be beyond our reach, receding into the interstellar void at 61 kilometers per second, unreachable by any spacecraft humanity could build with current technology. If we missed something important, we won't get a second chance. Europa Clipper's passage through the comet's tail will provide unique data. Direct sampling of cometary material by spacecraft instruments designed for Jupiter's environment. Not ideal, but better than nothing. The charged particles showering the spacecraft might reveal composition details invisible to remote observation. Or they might just be ice and dust, exactly as expected. We'll know when the data is transmitted back to Earth, assuming nothing interferes with communication, assuming the spacecraft survives the encounter unharmed. Mars orbiter observations from October filled the gap during solar conjunction. What they captured remains under analysis. Early results suggested normal cometary behavior, continued outgassing, no visible fragmentation. But early results aren't final conclusions, and normal doesn't mean expected when the object has been abnormal in so many other ways. The workshop scheduled for late November will bring together observers from across the globe, sharing data, comparing methodologies, refining orbital parameters. The location remains undisclosed to the public. Participation requires pre-registration, standard practice for professional conferences, or operational security for sensitive discussions. We won't know which until reports emerge, if they emerge. Some data will remain embargoed, protected by standard astronomical protocols that give research teams exclusive access before public release. 6 months, a year, however long it takes to publish findings in peer-reviewed journals.
Other data might remain classified. Not because it's dangerous, but because it's operationally sensitive, because it reveals detection capabilities or analysis methods that defense agencies prefer to keep private. The distinction between embargoed and classified is subtle but important. Embargoed data will eventually be released. Classified data might never see daylight. By March 2026, 3I Atlas will pass Jupiter, another opportunity for observation. The gas giant's powerful magnetosphere might interact with the comet's coma in detectable ways. Juno, NASA's Jupiter orbiter, could potentially contribute observations if mission planners decide the science justifies the effort. After that, nothing. The comet will continue outward past Saturn, past Uranus and Neptune, eventually crossing the heliosphere where the Sun's influence ends and true interstellar space begins. Decades from now, it might pass close to another star. Centuries, millennia. The timescales become meaningless at interstellar distances. Somewhere in that vast darkness, 3I Atlas will drift until gravity or collision alters its path, or until it reaches whatever destination it was sent toward, if destinations were ever part of its purpose. We'll never know. The observation campaign will conclude. The data will be archived. Papers will be published. Conferences will discuss findings. And eventually, attention will shift to the next discovery, the next asteroid requiring tracking, the next comet approaching the Sun. Until another interstellar visitor arrives, because they will arrive. Our detection capabilities ensure that. 3 in 8 years suggests we should expect more. Perhaps one every 2 or 3 years as survey networks improve. Perhaps more frequently than that. Each one will be unique. Each will raise new questions. And each will test whether our frameworks for understanding what arrives from beyond are adequate. Or whether we're still looking for natural explanations when the truth has already moved beyond natural.
October 29, 2025. 3I Atlas reached perihelion. Closest approach to the Sun. A moment of maximum energy. We couldn't see it. Solar conjunction obscured the view. Whatever happened during those critical hours happened without witnesses. Now it's leaving, fading into the darkness from which it came. NASA says it posed no threat. The trajectory is clear. The distance is safe. Everything is fine. But defense systems mobilized. Observation campaigns launched. Classified assets reoriented. Perhaps they were being cautious. Perhaps they were testing coordination. Perhaps they were preparing for threats we haven't been told about. Or perhaps they know something about what's passing through our solar system that hasn't made it into press releases. 3I Atlas will fade from view by early 2026. The questions it raised will remain. And when the next interstellar visitor arrives, we'll face the same uncertainty, the same gap between official assurances and observable actions, the same quiet preparation for something unnamed. If you found this journey through cosmic mystery compelling, there's more to explore. The universe doesn't stop being strange just because one comet leaves our view. Other mysteries wait in the darkness. Other visitors will arrive. And perhaps, if we pay close enough attention, we'll finally understand what they're trying to tell us, or what they're trying to hide.